starting the webinar, today's webinar. Let's to share the screen. So today's webinar topic is basically on introduction of CFD. So in this, we will be learning that what is CFD, how we are using CFD, where we are using CFD, and what are the various applications of the CFDs. So let's get started and understand what basically this is. Okay, so here before going to understand what fluidity, it is very much important to know what is fluid dynamics. So fluid dynamics is basically a branch of science which that studies how fluid like air or water moves in real life. So we can study here the fluid flow in three main ways, like the experimental way, theoretical way, or even we can use computational fluid dynamic ways as well. So in experimental way, this basically involves real life experiments to see how this one was. Okay, sorry for interruption. So in experimental way, these involves. Okay, so in experimental fluid dynamics, basically which involves a real life experiment. In this, we see how the fluid behaves in real life. So it is like very realistic, and but it is also on the other hand, if you see, it is very much expensive and tricky to measure the data accurately. But if we go for the theoretical point of view, this uses some formulas or maths to predict the fluid behavior, and it is basically a clean and straightforward, but like it is used in for a simple cases. If complex cases arises, then this theoretical fluid dynamics may gives an inaccurate result. So we go for the computational fluid dynamics. So this uses computer. With the help of computer, basically we simulate how the fluid moves in real life, what are its behavior, how will it behave in a certain conditions. So this types of simulations is helpful for solving the complex situations, and also it is very cost effective and fast. So but on the other hand, it has some errors and challenges like with the boundary condition and all things. So every method, like experimental method, theoretical method, or computational method, these all have its own advantage and also disadvantages. So if we'll go for the advantage and disadvantage of experimental method, so the advantage is that this method is very realistic and it involves like actual physical experiments. But the disadvantage is that it requires more equipments and can be expensive and sometimes measure accurately in like accuracy is very much difficult in this approach. But if we'll go for analytical method, so here the advantage, this like the advantage is that we use a clear formulas and general information, and we can solve simple problems which are straightforward, and the solution is also exact if the problem is very simple. But disadvantage that we cannot use like in a complex problem. It is only restricted to the some linear problems only. In numerical problems, like numerical method, basically CFD follows a numerical method. So the advantage is that in this method, like it can handle a complex shapes and also a complex like physics concepts also it can use. And and also side by side it is very much cost effective, and also our like the solution is also what we get is very much like in a very fast solution we get. But the disadvantage is that it can have a like errors due to rounding of the numbers, and like dealing with the boundary conditions can be like tricky, because inaccurate boundary conditions may lead to inaccurate in the uh, results. So now what is CFD basically? So like CFD is a field that uses computer to predict how like fluid like air and water moves and interact with their surroundings. It is also helpful to understand the heat transfer, mass transfer, chemical reaction, and other related phenomena as well. So to do this, like CFD solve complex mathematical equations that describes these processes. Now, how this CFD works, like we use, so in CFD, basically we use a mathematical model, like which is based on fundamental principles like conservation of mass, momentum, and energy. These are three fundamental equations which basically we are using and making a mathematical model. And these equations describe how the fluid flows and behave under the certain conditions. So we uses the like numerical method to solve these equations with the help of softwares installed in the computers. And this means like breaking down, like after that what we break down the fluid domain into number of pieces, which is known as like grid, we say grid, and calculate the fluid behavior at each pieces, like pieces or each grids, we can say that how this fluid behaves. So the result from like CFD analysis provide a crucial data that we are used in a various way. Like CFD like help us to like test and visualize new design early in the development process before like physical prototype are made, so this can save the time and the resources as well. Even in the detailed product development, it allow for the fine tuning and optimization in product development. Like for example, like CFD can improve the aerodynamic of car or the efficiency of the cooling system. uh, Also CFD in troubleshooting, it helps in troubleshooting also when there is a problem with an existing design. So CFD can help identifying the issues and test solution virtually. Even when there is a redesign in a product which is already exists. So this the concept of CFD like helps to like improve or modified it more effectively by providing like insight how changes will affect the performance. So after how CFD works, why we use CFD? These are like this question arises: why do we use CFD? So the use of CFD is basically incredible for the various reasons. For there are various alternates to the experiment, CFD offers a various alternate for the experiments. Like physical experiment can be very expensive, so CFD allow us to simulate these experiment on computers, for like we can save lots amount of cost. So CFD is useful in that sense. It also set up and conduct experimental experiments can since experiments can take lots of times. Experimental process can take lot of times. So CFD is time saving as well. And some experiments are very like could be dangerous, so we can use CFD to study this situation safely on the computer software. And it also very much feasible in some cases, like conducting physical experiment might be impossible like to due to some constraint, so CFD provides a practical solutions which is alternate to the experiment. So even like theoretical method often can only handle simplified problems, like CFD can tackle more complex and like the real life scenarios. So these are also where we like advantage for us to use CFD comparative to the experimental way. Even CFD works alongside with even sometimes we combine all the things and work with experiment and theoretical also to provide a more complete understanding of the project or the concepts. So in the sector of design and development, we use CFD to design and improve the product also, such as optimizing the aerodynamic of car or efficiency of the heating elements. Or if we go for the academic point of view, researchers are also using CFD to study the behavior of the fluid and try to discover new innovations which not has been introduced nowadays. And in education also, in colleges also, CFDs are used as a teaching tool to help various students understanding what is fluid dynamics and how we can relate this with the various projects phenomena. So nowadays, as we see that the use of CFD is has steadily growing, particularly in the design area. So today, up to 40% of design works are involved with the CFD, and which highlights the importance of modern engineering and development. So these are the applications where the CFDs are currently used. So the this concept utilized across these CFD applications are used in the various field to simulate fluid and fluid flow, even the heat flow, also heat transfer. So here are the some in aerospace, CFD are used for an application here F18 store separation is given, where it help us to CFD help us to predict and analyze the behavior of weapons, or you can where to store and how we can detach from the aircraft, to ensure the safety and the performance. And in automotive industry, we see there are various applications, but specifically we'll go CFD helps to helps in improving vehicle aerodynamic by simulating the airflow over the car surface to reduce how much we can reduce the drag to enhance the fuel efficiency. But and in biomedical also, CFD model temperature district, CFD is used for the model temperature distribution and natural convection current in the eye when we are using a laser heating. And this basically help us to understand the thermal effect and the optimized medical procedures to what we can use it. And in even in chemical processing, HVAC and hydraulics, CFD are used in. So in chemical processing, CFD basically are used in the polymerization reactor vessel, to predict the flow separations and recite the time effects, which is crucial for optimizing the mixing and the reaction rates. Also ensures uniform product quality and prevent issues like dead zone or overheating. So these all CFD's concepts are also used in chemical processing. Even in heating, ventilation and air conditions, CFD helps in designing efficient ventilation systems by analyzing streamline from for workstation ventilations. This ensures that the air distribution have a proper effective flow, provide a comfort and health environment, that how this flow can remove the contaminant and maintain the desired temperature and airflow. Even in dams and hydraulics, the concept of fluid, the concept of CFD is used. It's employed the study of scout downstreaming of flood control structure. So by stimulating water flow and sediment transport, engineers like we as an engineer can predict erosion patterns and design measures to protect the structure from the data from damage, and ensures the longevity and the safety of the flood control system. And even in marine, oil and gases, power generation, sports, and nowadays in EVs, new technology emerging like EVs, we are using CFDs. Like in marine industries, in oil generation, like in oil, CFD models models the flow of lubrication mud over the drill bit. This simulations ensures that the how efficient cooling and lubrication is done, which reduce wear and tear on the drill bit and enhance the drill bit performance. Even in power generation, also CFD concept is used, where we analyze the flow of like air around the cooling tower, which simulates the airflow and heat transfer and helps design more efficient and cooling system, which basically optimize the thermal performance and reduce the energy consumption in the power plant. Even the sports sector also, like CFD is used like the flow that the fluid flow around the ball to understand and optimize their aerodynamic design, which includes like analyze how the airflow affect the ball's trajectory or spins stability. So these all applications are there where CFDs nowadays are used. So now how CFD works, how we can use this CFD, and basically how this works in a various softwares, and what we do, how we initiate in the CFD analysis, and what we can get after the analysis part. Computations fluid dynamics like works by simulating a fluid flow and heat transfer using numerical analysis as well as the some algorithms. So there are the some steps that how CFD operates. So the process basically begins with developing a mathematical model of a physical problem. So here, an example has shown that the bottle filling scenario, that the model includes bottle, filling nozzle, and the fluid like water is there being poured into the bottle. So model is based on the principle of the this model is basically based on the principle of fluid dynamics. So the fundamental like equation, like governing equation flow, which we will be using in current example, like conservation of matter, that is continuity equation, momentum equation, that is momentum equation, like the Navier-Stokes equation, and other energy equations. So these equations basically should be satisfied throughout the entire region of the interest, which in case include the inside of the bottle or the space around the nozzle. So the properties of this fluid, like the fluid which is there inside the bottle, viscosity, the properties like viscosity, or we can say the density, are basically defined empirically with the help of experimental data. So these property also influence that how fluid behaves under various conditions, such as different at different flow rate and pressure. So to sometime what we do to make the the problem trackable. So we in some scenario we simplify it by taking some assumptions, for example the problem we can might assume as a steady state, the condition at which the property do not change over time. We can also consider incompressible flow, like the fluid density is constant, or we can also consider inviscid, where we consider that the viscosity is negligible, or we can go for two-dimensional flow also. So there are various assumptions also according to the complexity of the problem. We can also take some assumptions which do not impact the output result. So these assumptions basically what we do, helps to reduce the complexity of the equation to solve in the CFD and software. Even appropriate initial and the boundary conditions are provided to define the state of the fluid at the start of the simulation, and the behavior at the boundary of the domain. So in the bottle filling problem, we say initial condition might be include the initial air or a water level in the bottle, or while if you go for the boundary condition, it could be the flow of water from the nozzle and the pressure at the bottle on the top. So these are the steps that how we should know how to start any CFD problem. So mathematical model is one of the initial step. Before that also, in upcoming slide, I will be explaining that what are the basic steps that we need to follow to solve a CFD problems. But here at present, mathematical model is the initial step we should consider. Now, after that, in CFD, like numerical, like numerical method are used to approximate the governing equation. So what the governing equation, in the partial differential form, we have of the fluid mechanics, we have made in a interest of a region where we want to find the result. So these governing equations are basically are differential equation, and these equation is being transformed into an algebraic equation. So this all basically is done in the by the process of discretization. So the continuous when the continuous fluid region, this continuous fluid region basically, like in case of bottle filling problem, this the region is divided into finite number of small elements or cell, and these small number of elements or cells basically forms a grid, or we can say a mesh. So this step basically continues the this step basically converts the this continuous partial differential equation into a set of discrete algebraic equation, and that can be solved numerically. So the collection of these cells, which is also known as grid, each cell in this each cell represent a small volume of fluid domain, and the property which within these cells are approximate using a numerical method concept. So the discretized algebraic equations are solved numerically using a software softwares in the computer, and the equations are formulated in such a way that the flow field variable like velocity, if you go for velocity, pressure, or temperature, are calculated at each node or the cell within the grid. So the this system of algebraic equation is typically solved simultaneously, so that we can ensure that the consistency and the accuracy of the result is maintained. So after that, after obtaining the numerical solution, the data is post processed. What is post process, I will explain in the upcoming slides. So for now, after obtaining the numerical solution, the data is post processed, to extract the quantities of interest, this in post process. Basically we visualize the data, that how does it looks in real life, suppose how the velocity will looks how the pressure difference over the domains is looks, and other relevant metrics is such as pressure loss, heat transfer rates, and flow patterns as well. So these post processing help us to analyze and optimize the fluid system uh, to study in better way. Now, after modeling fluid flow involves here we are using a governing equation of fluid mechanics. Primarily the we are using a Navier-Stokes equation, the continuity equation, and the equation of states. Like yeah, so these are the governing equations what basically we are using in a modeling the uh, governing equation of a fluid mechanics. So we are using a Navier-Stokes equation, continuity equation, or and also an equation of states we are using it. So these if we go for the Navier-Stokes equation, so this equation basically describes how the velocity of the fluid evolves over time, and and also in space. So in here the equations are in 3D three-dimensional Cartesian coordinates, like x-axis, y-axis, and z-axis, all the axes as given. So they account these equations accounts various forces acting on the fluid. So if we go step by step, what is local acceleration? So these terms basically represent the rate of change of velocity at the specific point in a fluid over a time. If we and the convection, basically this term accounts for the movement of the fluid from one place to another, which carries the properties like momentum, energy within it. Even the piezometric pressure gradient, so these represent the pressure acting on a fluid, like driving it to move from high to the low pressure region. When there is a pressure region, like a pressure difference, so it represent the like pressure force, how much pressure force is acting on the fluid. The if we go for the viscous term, so these terms like account for the internal frictions within the fluid due to its viscosity, which resists the flow and the dissipation energy. So even we are using a continuity equation also in the CFD flow analysis. So these equation basically ensure the conservation of mass in the fluid flow. So it states that the mass entering into in a control volume must be equal to the mass leave it. So mathematically, we say it ensures that the sum of the inflow and outflow of a mass in any part of the fluid is zero. So, and also equation of state, like we're using equation of state concepts also, like in CFD, CFD, like it basically relates the fluid density and other with the other. It relates like the fluid density with other properties like pressure and temperature. So this is a broad diagram on that how CFD code works in the software, because basically we perform an analysis in the software. There are various software, different softwares like in ANSYS Fluent, in Abacus. So in ANSYS Fluent, that how this CFD code works in the background is like we should know that how what step we have to follow to like analyze any of the problems what we have in a CFD software. So this code basically is designed around the numerical algorithm that can solve fluid like flow problems. So this code typically consists of three main elements like pre-processing, solver, and a post-processing. So in pre-processing, if we go, is that where the users like enters the detail of the fluid flow problems into a CFD problems, and the input data is then transformed into a format of solver that can work behind the software. So in pre-processing, basically we have a different steps in pre-processing. So in pre-processing, first what we do, we define the geometry of the computation domain, like the region of the interest where we want to analyze. And after that, we will be generating a mesh of smaller or non-overlapping like domains within the computational domain. And after generating a mesh, we select the physical and chemical phenomena which is to be modeled. And after that, we will be defining the fluid property and specifically appropriate initial and boundary conditions. So these are the some steps which we have to follow in the pre-processing while analyzing in the CFD. So like defining a geometry, generating a mesh, then fluid property, physical model, and defining the physical model and initial and boundary conditions. After that, after that, uh, the second step is the solver part. So the solver basically is a core component of this CFD code. So it takes all the governing equations that we have discussed before, like Navier-Stokes equations, continuity equations, and state equations, and applies them to each small volume, or we can say a control volume in the fluid domain. So there are various steps involved in this solver. So the first step is the approximation of unknowns variable such as velocity, pressure, temperature at some discrete point within the fluid region. And in this step, basically the continuous governing equations we are basically being transformed into a discrete algebraic equation. And this is done by substituting the approximation in the governing equation and manipulating them accordingly. So this step involved breaking down the fluid domain into the grid or a mesh in a small cells or a control volume. And finally, the solver and after doing this, The solver finally uses numerical method to solve the resulting algebraic equation in every nodes. And this is typically done like iteratively until the convergence solution is found. So, like convergence solution found means we can say that the changes between the iteration become negligible, very much small. So, there are various methodologies which are used uh, in CFD, like during solving the solution of finding the solution of CFD problem. So methodologies are finite difference method, finite volume method, and finite element method. So these are the three numerical method we say which we are using in analyzing the problems in a CFD. So in finite difference method, this method basically approximate the derivatives in the governing equation, which are using a difference between the neighboring grid points. And it is very much straightforward but less flexible for complex geometry. And if we go for like finite volume method, this is the, you can say, the most commonly method which is used like in a commercial CFD software, like in Fluent, CFS, the next. And it involves like what, how does it work? It involves integrating the governing equation over the each control volume, which ensures the conservation of mass, movement, and energy is applied over all whole control volume. And this method is very much highly flexible and well suited for the complex geometry. Even finite element method is also used in a CFD analysis. But this method, basically what happens in this method, the fluid domain is divided into the mesh of the element and uses like polynomial equations like safe functions to solve the governing equation. And it is also very much powerful, like concepts for handling the complex boundaries and different at also the materials also very much like different properties is different. This method is also used very much. So, like finite difference method, basically this is a historical significance in computational fluid dynamics. Like due to its simplicity and like ease of programming, it works by approximating the like how does it works? It basically it approximates the derivatives in the governing equation, which uses differences between the neighboring grid points. So this method is straightforward and in early development of CFD, this method was used very widely. And if we say that FDM is one of the first, like we can say the first numerical method developed for solving the partial differential equation in fluid dynamics. So FDM, like this method basically nowadays are very much less or you can say negligibly used in CFD analysis. Why? Because it cannot, so it's face a struggle while solving the complex geometry problems, and it's and also it requires a structured grid arrangement and which are not flexible enough for irregular shapes. So in modern CFD application often basically deals with integrated or we can say irregular complex domain. So where like nowadays we are using a finite volume method or finite element method is also used in some cases for more flexible and like and flexible and suitable complex design. In finite element method, so these like this method is basically widely used in structural analysis of solid, but some in some applications it is also used in fluid dynamics also. So how does it work in FEM method? Basically we divide the fluid or you can say the solid domain into a mesh of smaller or simple shape, which is like here we call that shape as an element, and using a polynomial function like shape function to approximate the solution within each elements. So FEM is basically known for its stability and especially in solving complex structure problems. FEM, like in FEM is a very great method, and it provides a very accurate result. But the problem is FEM basically requires more memory and also has a slower solution process compared to the finite volume method. So this makes it less efficient for larger scale fluid flow problem that are most common in CFD. So the finite volume method is nowadays using a like it's a popular approach used in like computational fluid dynamic concepts because the efficiency and accuracy of the result. So it is known for its efficient memory usage and fast solution speed. So which make it ideal for the large scale problems and like scenarios with high Rayleigh numbers, turbulent flow, or the source term like dominated like which are dominant food like combustion. In the combustion flow also it gives a very like it requires less memory and gives fast solution. So and in FVM, basically, the governing equation, like the partial difference governing equation, like Navier-Stokes equations, we can reformulate in the conservative form. Like this means they can express in terms of conservation law or ensures that the important physical properties like mass, momentum, and energy are conserved within a discrete control volume. So in FVM, the fluid domain basically is divided into a grid or mesh, or we can say small control volume. And these volumes basically encompasses a specific region of a fluid domain. And the governing equations are solved within this each volume. So within each this control volume, the conservation equation ensures that the fluxes of mass, momentum, and energy equations are conserved within each volume. And this means that if there is any change in one property like mass, flow rate, or we can say the velocity within the volume, it should be balanced by corresponding change in the other properties. So this is how the steps in finite volume method is done. Now, after after pre-processing and solver, the next step is post-processing. So what is post-processing basically? So if we say post-processing in CFD is you can say it's like a translator. That basically what it do, it takes a raw data from the solver, the data the solver solved at a particular what we need, and these post processor what it do turns it into the visual representation result like which we can easily understand. So it presents the outputs in the form of tables, graphs, or images. So we can consider an example like it can show contours which are like maps showing how properties like velocity and pressure varies across the simulation domain. Even line plot we can use display how property changes along a specific line in a domain. And in post processing we can go for a vector plot which shows the direction and a magnitude of a flow at a different point. In surface plot we can reveal that the surface and surface shapes and characteristics of the surface within the domain, that how does it look. Lastly, we can also do go for the particle tracks. So which can illustrate the movement of the particle throughout the fluid region, that how the particle is moving throughout the fluid. So these visualization basically help us to analyze and interpret the simulation result, and making us to inform decisions and improve the design of the process. So these are some basic steps, not that while solving on a specific problem uh, with the help of CFD. So what are these basic steps? Like first we have to identify the problem, that on what problem we have to analyze, we have to do the analysis. And after identifying the problem, we have to follow several steps, like we have to define a modeling goal, identify a domain, like which domain we have to model, design. We have to design like it's a pre-processing part. Then we have to form a grid like discretization. After that, this process solver execution in which we set up a numerical model, compute and monitor the solution, and then post processing where we can examine the result what we actually want. So let's go step by step understand this. Like in this analysis, like the basic step involved is defining the modeling goal. So considering modeling options like incorporating necessaries physical model and making simplified assumptions and determine required accuracy and speed of the result. So we have to identify the specific result what we are looking for, such as pressure drop or mass flow rate, and also we need to understand how they will be used in the design or analysis process. Even also Even also, we have to explore different approaches and techniques which are available in the CFD modeling, which can consider various numeric method and how we can solve, uh, use the various algorithm to solve the solution. Even we have to decide which physical phenomena need to be included in the analysis, such as like turbulency, compressibility, or radiation, based on the characteristic of the problem. After that, we need to determine that is is there any we can go for the simplification or reception that can made to streamline the analysis while maintaining the acceptable accuracy of a problem. After defining the after defining the modeling goal, we have to the domain identify the domain what we will model in a crucial step in CFD analysis. Like it involves isolating a specific part of a complete physical system for a detailed study. So we need to determine the section of the system which we need to model. Like for example, suppose if we want to study the airflow of flow around a car, so we need to know that that the domain what we have to select, that the car body we have to select, the whole car we have to select. So it depends that what section we are choosing to to model the car. So now after that we have to establish the computational domain, from where it begins and from where it ends. So which this involves like deciding on which on the physical limits of your of the model, such as in what are the inlets, what are the out, like in flow of car. So what is the flow of direction flow of the car? What is the direction flow of air? Direction of car? What is the velocity of the car? These all are things which need to determine. Even we should if after determining the domain, we should also know or consider that if the problem can be simplified, like for instance can be approximate as a 2D problem, or we can say an axis symmetry problem to reduce, so that we can reduce the computational effort without sacrificing any accuracy. So these are the identification of domain and the steps that we need to follow during the analysis of analysis in CFD. So while designing and creating the grid in the CFD analysis, we need to choose the appropriate grid based on the complexity of the geometry and fluid, uh, to required resolution and available computation resources. So grids, there are several types of grids, like we can mesh or we grids or mesh. So like quadrilateral there are quadrilateral, triangular, tetrahedral, hexahedral, pyramid, prism or vest. These are different types of grid selections. So for simpler or structural geometry, we basically use quadrilateral or hexahedral grid, and these are basically efficient and provide high accuracy for like and flow for aligned flow region. Even for more complex and unstructured geometry, we are using a triangle or tetrahedral grid. So they are more flexible and can easily conform the integrate shape. So that's why we are using there this types of grid arrangement. Even we are using a hybrid grid arrangement also. So which in that basically which combines different types of elements like hexahedron or tetrahedron, prism or wedge to balance the accuracy and computational efficiency. So there are various there are various steps like we have to access the geometry's complexity to decide on the grid type, like which type of grid we have to use. We have to determine if the like conformal interface, like where different grids are made, is needed to handle complex boundaries. We have to ensure that the like grid resolution is fine enough to capture the geometry accurately and predict regions with high gradient. Or also we have to during this process we have to like use grid adaptation technique to like refine the grid in the area where the resolution is needed or not. So these are the various steps that we have to select according to the complexity of the geometry. So that we need a fine grid, or we need to go with the less finer or coarse grain, we will be getting the result accurate or accurately or not. So these are the some steps. After this, now setting up the numerical model in CFDs also involves several key steps to ensure like accurate and efficient simulations. Like we have to select an appropriate physical model also. So in this segment, the necessary like physical model for our problem. Like for example, if our modeling turbulent, if our we are modeling turbulent flow, so we should choose turbulent model. Or suppose if we are dealing with some combustion or multi-phase problems like liquid and gas, we should select an appropriate model according to that. After
Neeraj,
that,
mute yourself.
we
Neeraj,
should
mute yourself.
steps that how we can specify the fluid properties which is involved in the simulation process. Like we should define the fluid properties like density, viscosity, and thermal conductivity. Even if there is a solid boundary or an object, we should define the thermal or mechanical properties of that also. If we are using both solid and liquid, so uh, if the our problem basically involves both concepts like solid and liquid concept, so we need to specify the property of the mixture. So these are the certain steps that we need to check during the numerical model, that what are the needs of our analysis, like whether we are focusing on the fluid or solid or a mixture. After that we have to like we need to know the how to define the boundary conditions of the domain. For example, the specific velocity at the inlet, pressure at the outlet, even no slip condition in the solid wall. So these are the we have to prescribe the operating conditions. After that we have to know that what are we have to provide an initial condition also. Like we can start with the initial guess for the solution, and this helps basically the solver to begin with the iteration process. And a good initial guess can also basically speed up the convergence. And after that step, like setup control, solver control, like we can configure the numerical solver settings, like such as time, step size, iterations limit, or and these like settings control how progressively like through the we can find the solution progressively and accurately. After that we now after that like computation the solution, like this compute and monitoring the solution, this is also done in the solver execution only. So computing the solution of the CFD basically involves solving the discretized conservation equation iteratively until the convergence is reached. So these solvers basically goes through multiple iterations progressively, updating the solution variables like velocity, pressure, and this like solution goes until the these properties do not get stabilized. So we should like convergence is reached, we should know how we can reach to the convergence. So convergence is basically achieved like when the changes in the solution variables like between the iterations become very small. And this is achieved how, like residuals basically, which is a numerical value. uh, this help us to monitor the convergence. So they, it should be decreased to low for the stable, or the less the residual, the more accuracy and the accurate the result will be. And conversion will also come very uh, early. So ensuring like after that, uh, like the accuracy of the convergent solution basically depends on what. So it basically depends on the physical model. So we should use appropriate and accurate model for the phenomena, like just suppose turbulency, heat transfer, or multi-phase problems also. Even grid resolution and independence factor also affect the accuracy. So we should ensure that the grid is fine enough to like capture the important details, but not so fine. The grid should not so fine that it like basically waste the computational resource also. So to check that the solution doesn't change significantly, we go for a grid independence test. Even after like we can say that a converse or grid independent solution to the to a well defined problem will yield accurate and useful engineering results. So after solver, these are the steps like post processing what we after like computing the solution in the CFD analysis. So the result is examined, and this is a crucial step to ensure the accuracy and the usefulness of the data. So we use a visual tools like flow patterns to visual the overall flow patterns to understand how the fluid moves through the domain. Even we can check the area where the flow separates from the surface, which can indicate inefficiencies or design issues. Even we can identify the region where the shocks, shear layers, or any other critical like flow features like to assess the impact of the performance. So so these are the like steps that we need to see that is there any separations or shocks, are the flow like features are resolved. These are the question we have to see during the examination of the result. And finally like after finally that and we should can assure that the property like conservation and correct physical behavior of examination the result. If the residual are high, if see that the residuals high, like the investigate area will be of poor quality cells that might cause issue. So proper examination of result ensures that reliable and accurate engineering insights. So there are like during this process, this computation fluid dynamics basically offer a several advantages that makes it invaluable tool like in engineering and designs. The first is relatively low cost. So in traditional we see the physical experiment and test where the test tasks required to gather essential engineering data can be very expensive. So these includes like more cost, and we have to build a prototype also, conduct wind tunnel test also, like in aerodynamic. If suppose we want to check the aerodynamic behavior, so we have to conduct a wind tunnel test, and we have to set up a very large experimental lab. So CFD simulation, on the other hand, has a much like more cost effective, and the primary expense in this CFD involves the software and computing resource, but these are generally like lower comparative to the like physical testing. And additionally, we say computational power continues to grow and become more affordable, like the cost effectiveness of CFD simulation is further enhanced. If we see the advantage in terms of speed, like CFD simulation can perform like relatively quicker compared to the time required to set up and conduct a physical experiment. So this quick turnaround is basically particular beneficial in the early stage of the design process, where we can rapid iteration and optimization are necessary. But the engineers basically can test multiple design variations and can access their performance without the delay of like physical prototyping. So the ability to obtain like fast result accelerates the overall development cycle, allowing like for more innovation solution and timely project. Like if we have some project, we can timely complete it. Even even the third advantage, like ability to simulate real like time conditions. So certain flows and heat transfer process are challenging or even impossible to replicate in a like physical environment. Example, like we can take an example like hypersonic flow, which occurs at very high speed, and that is greater than 5 times the speed of the sound, or complex thermal interactions within the largest system. So CFD allow engineers like to theoretically simulate any physical conditions, which provide insights into scenarios that are otherwise difficult to like test. So this includes like extreme conditions such as high speed aerodynamic, micro scale fluid flow, and multi-phase. So by using CFD, we can analyze and predict the behavior of the system under various conditions, enhancing the understanding of the phenomena like that would impractical to observe experimentally. Now, even we can in ideal scenario also, CFD analysis have a ability to simulate the domain or the product what we want to analyze. So CFD basically gives precise control over the physical process that is being simulated. So this control allow them to like isolate and study specific phenomena without the interference of external factor. Even CFD provides a comprehensive evaluation informations. Like if we go for the physical experiment, which are often limited in the amount and the location, amount and the location of data they like we are collecting. Since but CFD, however, basically provides detailed data across the entire simulation domain, and which include the comprehensive flow parameters like velocity, pressure, temperature, or we can go for like turbulence quantities at the numerous location within the region of interest. So these are the various advantages of CFD. But while CFD, as we know, it's a powerful tool, but it does have some limitations. Like the one is the physical model. So CFD simulation basically rely heavily on the physical models to represent like real world process, like turbulence model, compressibility, chemical reactions, and multi-phase problem. So the accuracy of the CFD solution is directly tied up to the like accuracy of these models. So if the models are not well developed or do not capture the true nature of the like physical phenomena, the result will be inaccurate. Even numerical errors is also there. like like round of error, truncational error. So in round of error, these type of errors basically arises because like in computer software, we have a finite word size, like meaning, which means that it can only stores with certain level of precisions. So although it round up the errors and generally it is generally small, but it is also calculated as error only. And in truncational errors, this error basically occurs due to the numerical method when the after solvers solves the equations and involves approximation concepts. So the derivatives in the governing equations are approximated by differences on a grid, which introduce a truncational error. So if the truncation error decreases as we refine the grid, meaning that the mesh size is made smaller and the approximation become closer to the exact value. And however, the refining the grid increase computational cost and time. So this is the some of the limitations of CFD. So another limitation is the boundary conditions. Boundary conditions basically are critical in CFD solutions, as they significantly impact the accuracy of the result. Just physical model, the accuracy of the CFD solution is only good as the boundary condition provided. Like for example, if we consider the flow in a duct with a sudden expansion, if the flow enters a domain from a pipe, usually fully developed a velocity profile, which represent the realistic distribution of velocity across the pipe cross section, and it is very and is essential. So assuming a uniform flow instead can lead to an inaccurate prediction of flow behavior, such as pressure drop and separation result. So proper boundary condition ensures the simulation accurately, which represent the physical scenario and which leads to more reliable and useful results. So these are the limitations of CFD analysis, and this is all about the introduction of CFD, the basic concepts like how CFD works, what is CFD, what are the process, what are the steps we need to follow during the CFD analysis. So thank you very much.
Anybody do you have any question? You can ask.
What is hello, hello, sir. Hello,
Hello.
I am Neeraj Kumar. So I want to
Yeah,
know
hello, you're audible.
I am operating NC School for the problem solving in the
Yeah,
solar distillation problem. But here I have faced many problems regarding post processor of solar distillation, like mass flow rate with the time, all these. Have you any separate session for that for post processor?
your voice is
How
not
to
audible.
operate the tool?
Your voice is not.
Sorry.
Your voice is not audible. It's not clear.
Now it is audible.
Like, now it's audible. Yeah, it's
Yes.
breaking.
I want to say that these are basic concept. I thank you. You have explained very nicely. But I have a question. I am operating. I am apply CFD uh, fluent package in solving the problem of solar distillation. But still I have faced some some problem regarding the post processor, like the plotting. So there is any available separate video for that? There is the available session for that?
Uh, Currently, we don't have, but in future, if we have the separate session, we will be letting you know, and then you can join and like understand how the steps follows.
Yes, particularly I am facing problem regarding post processor of solar distillation. How to plot the
So,
mass flow rate with times is all these things I have faced temperature plot, pressure plot with the time.
so for that, basically, you have to when we will
I
be
am
having a
solving the
session.
time dependent problem. Yes, sorry, sir.
So what I'm saying that like you're solving a steady state or unsteady state, and one thing that
Unsteady state, time dependent,
unsteady
time
state.
dependent.
Okay, like transient state, right? So,
Yeah, yeah.
when we have a session on the SolidWorks, like ANSYS software, when we're working on the software, at that time I can help you out because currently I don't know, haven't seen your like design, how you have made, what are the inputs you have given. So I cannot comment on right now that how, what uh, problem, like what mistakes you're doing and why you're not able to plot it. So when there will be a session on ANSYS software, then I think I can help you out at that time.
When will session held? That session, that particular session.
Currently, like we will be letting you know in future when it will be happening. Like you will be knowing before only. Like currently we don't have.
Okay, thank you.
Thanks, sir, for hosting the webinar. Your expertise and insight were invaluable for our learners. I would like to take the opportunity to introduce our company, ISI India product and services that we offer in EV technology with a small video. So kindly have a look on video. Actually, there is some error in the video. So thanks for joining in the webinar. Thanks a lot.
What about the feedback and attendance form, ma'am?
Sir, actually, hello. Hello.
No.
Sir, what is non-conformal interfacing?
Hello. Kindly send us inquiry through a QR code displayed on your screen and take your first step towards a more sustainable and exciting future.
Can we leave now?
Yes, you can leave it.
Thank you, ma'am.
Oh, what about feedback, ma'am?
You will receive the mail for the feedback also.
Okay, thank you.